Hello, I'm Eric Lepowsky from Princeton University, where I am advised by Professor Alex Glazer, and I will be presenting on our work toward autonomous robotic inspections of nuclear facilities. And this project is in close collaboration with Professor Rob Goldston at the Princeton Plasma Physics Laboratory. We draw motivation from a variety of potential applications, ranging from the safeguarding of uranium enrichment facilities to the verification of future arms control treaties. Both nuclear safeguards and arms control traditionally require intrusive on-site inspections to perform verification tasks. We are specifically interested in the task of localizing a radioactive source. In a scenario when no significant neutron emitters are expected or declared to be present, the ability to accurately identify a source in a timely manner is crucial. On the safeguard side, an example of this would be searching for a clandestine withdrawal station within the cascade hull of a gas centrifuge enrichment plant. On the arms control side, you could imagine needing to confirm the absence of undeclared warheads in a potentially secure storage facility. Now, protocols currently exist and methods have been proposed to perform such verification tasks, so what is the benefit of using robots instead of humans? The general idea is that autonomous mobile robots equipped with neutron detectors may be able to perform inspections of nuclear facilities with limited access and minimal revealed data, addressing both safety and security concerns. If designed properly, a robotic inspector may be even more effective and efficient and less intrusive than their human counterpart. As I've alluded to, this work has mission relevance to both safeguards and arms control. The project entails developing and implementing a new detector configuration in addition to considering how robots can be used to monitor the nuclear fuel cycle or be used to perform treaty verification. With that background established, I'll introduce our inspector bot, which you can see here. The inspector bot is comprised of 3 boron-coated straw detectors encased in a cylinder of high-density polyethylene and mounted on an omnidirectional robotic platform. A cross-section of the detector and moderator configuration is also shown, where you can see that the 3 detectors are equally distributed, as well as room for an additional 3 detectors which can be added in the future. While many reported methods for radioactive source localization rely on only the total detected counts, the detector configuration of our inspector bot provides us with directional and spectral sensitivity. The ratio between the counts from each detector is dependent on the energy of the source, the distance and angle to the source, as well as the surrounding environment. We've developed an MCNP model of the robot to extensively characterize the detector response, and we've benchmarked the model to experimental measurements taken at PPPL using a bare and moderated Californium 252 source. For localization purposes, we perform curve fitting of a simple first-order cosine model, which provides the estimated direction towards a source given a single set of measurements. The counts and direction are then used in the framework of a particle filter, where each particle represents a hypothesized source intensity and location and is assigned a weight according to a cumulative likelihood function. Here, I provide snapshots of what the particle filter looks like in action using MCNP-based simulated data. The top row demonstrates the case of particle filtering using only the gross count information, while the bottom row implements the directional information, which is unique to the design of our inspector bot. In both scenarios, at each iteration of the particle filtering algorithm, the robot takes a 1-meter step toward the center of mass of particles before acquiring a new set of measurements. By advancing the robot toward the source estimate, we are able to recursively estimate the posterior belief of the source parameters where the prior was simply uniformly distributed in space and source intensity. For the gross counts only case, the likelihood is based on a Poisson distribution. For adding the directional information, we use Poisson and von Mises distributions. What we show here is that by adding the directional information, the inspector bot is able to localize the source more efficiently and in fewer steps and with lower uncertainty. This project would not have been possible without the collaboration with PPPL, including the experimental campaign used for calibration, as well as planned future campaigns we hope to conduct to test the design with the algorithms which we are developing. To conclude, leveraging the directional sensitivity of our inspector bot correctly estimates the location and intensity of a source with fewer measurements as compared to particle filtering based on gross counts alone. The goal is to develop a system which can ultimately be used to autonomously perform verification inspections in support of the NNSA mission. A few next steps which we are actively pursuing include analyzing how background noise and obstacles affect the detector system and localization capabilities, implementing methods for motion planning which build on traditional robotics to factor in the uncertainties from the radiation detection aspect of the project, and finally investigating how we can leverage the spectral sensitivity of the detection system. And with that, I'd like to thank you for listening.